Welcome everyone. So what we want to do is look at a couple of examples from energy and reactions exercise number 3, where we're looking at energy diagrams and working through the math associated with both the activation energy and the delta H. So one of the things that we want to do is make sure that we understand where to find those values. And so when we look at activation energy, remember that activation energy, which we can call E sub A, is equal to the difference between the transition state and the reactants. And so here's our reactants over here on the left. Remember, our transition state is the top of our energy hill, and then we have our products over here on the right. And so for this first example, we can see that our activation energy is 90 kilojoules. Keep in mind that all activation energies are positive. They all represent the bonds that have to break to start the reaction. And so they're always an input of energy. Now, when we look at delta H, I think it helps to go ahead and do a quick analysis and see where your products are in relationship to your reactants. And so you can see here that we're working our way from reactants down to products. So this is going to be a negative delta H. Remember that delta H is always reactants minus products. And so our delta H here is going to be negative 71. And so make sure that you realize that this is, in fact, an exothermic reaction. And again, one of the ways that we can tell is that our products are lower in energy, or we could say that they are more stable. Now, we can think about this reaction going in the opposite direction. And so what we can do is we can think about, okay, let's take this is ethanol and our bromide, and let's go right back over the other way over the hill, right? And to do that, for an exothermic reaction, you have to first put in energy to get back up to your initial part, and then you still have to go over the hill. So in this case, you're going to have to add your 71 plus your 90 to get all the way back to the top of that hill. And so in this particular case, the activation energy is going to be 161 kilojoules. Now let's look at the second example, number 6 from your exercise book. So all of our definitions are the same from reaction 1. And so again, when we go to find our activation energy, our reactants are still here, our transition state still at the top of the hill, our products are still there, but now our hump is 184 kilojoules to get from reactants to the top of that hill. But when we look at this particular reaction, notice that to get from reactants to products, we are working our way up. And so our delta H here is going to have a positive value, in this case positive 13, because we have to add in energy to get to our products which are at a higher energy, right? And so now we have an endothermic process. And so when we think about this reaction in the reverse, to go from our hydrogen and our iodine back over that hill, right, we're only going from we're already part way up. And so to get our delta H, we're going, let me restate that. To get our activation energy for the reverse, what we want to do is we want to take our initial activation energy, so our activation energy for the forward reaction, and we want to subtract our delta H. And so we're going to take 184 minus 13, and so we're going to end up with 171 kilojoules for this particular example. And so work through the other exercises and pay special attention to when it's endothermic versus exothermic.